So, a big title here on big data. My name is Peter Nugent. I'm an astrophysicist, computational forced, I would say. When I went to graduate school 20 years ago, the big push at the time was getting department quote-unquote supercomputers. And these were things that were basically as powerful as your desktops today. And what I walked into was radiation hydrodynamics. I got caught on studying things which exploded. That was cool to me. I wanted to do rockets. I wanted to do the planets. My professor told me, no, that's geology. You want to do that, go down the hall, go talk to the geologist. You want to do astrophysics, study something bigger, study something that explodes, study the largest explosions in the universe. So that's what I did. And I went off from graduate school with this huge theoretical computational background in radiation hydro and walked into a group which wanted their token theorist. And this was Saul Perlmutter's group. And he said, you're going to be the guy that helps us interpret everything that we're seeing and helps us plan our next set of observations. And I said, great. This sounds like fun. This sounds exactly like what a theorist wants. A theorist always wants data so that they can confront it with their models. And then the next thing Saul said to me was, and oh, by the way, we're one person short on the next telescope run. Could you go down and do some observing for us? And I said, Saul, I've never been in a telescope other than, in my backyard. So what am I going to do? He said, don't worry, you'll pick it up pretty easy. A few years later, after observing many, many times, I got into the mode of, wait, I learned all this great computational stuff for doing these rad hydro simulations. Why can't I apply what I learned to processing data so that we can look at tackling problems which were much, much larger than people were thinking about at the time? And so that's what I'm going to talk to you today about, the Palomar Transient Factory and some of the things that we've been doing there and how we've applied the things that I learned when I went off in grad school in a totally different area to a new problem, which is tackling pipelines and large data processing and trying to get the most out of it. I'm going to take a little sidestep for the first few slides because the next thing in computing, of course, is something that you guys are going to suffer through. I suffered through this when I was in graduate school. When I started off, there were these little nice crays that we never actually got to see. They sat in some basement in some building somewhere. And we learned how to program on those. And there was no such thing as MPI or OpenMP. And then that happened while I was in grad school. And I had to learn it. Well, you guys are going to be stuck with the same problem. You guys, if you haven't already, you're going to have to start thinking about processing on accelerators. And so I'm going to take a few side steps there to show how this will impact you and your area, then go off and do the data portion of the talk, and then come back and how these two may or may not merge, okay? And how you're going to be stuck solving the problem because I'm too old to learn a new language. So these are the big problems in the future in HPC, okay? Power. You guys ever gone to a supercomputing facility and looked how much power these things suck down? NERSC, which isn't large by any stretch, is 9 megawatts coming into the building, okay? That's a hefty bill that you have to pay every single year. Data. Everybody here will know by the end of this talk, if they don't know already, that data and what we do with experiments and sensor collecting and you name it is increasing dramatically. Programming. If we want to switch to some of these new things like programming on GPUs, etc., well, there's a steep learning curve for that, and we've got to get ready for that. And all of these things hit your wallet at the end of the day. Okay, you've got to pay for the electric bills, you've got to pay for your hard drives, your solid state drives, your tapes, whatever you're going to do it. You've got to train people to learn new languages. You've got to optimize those languages to get the most out of your machines. All of these are expensive. So if you look right here in the past past decade to the next decade, and you look at the number of teraflops, this is a NERSC right here and where we're headed. And, you know, this is where the top 500 is, and usually the big machine at NERSC is just, you know, in the top 10, top 5, somewhere there for a while. And so the big question comes is, you know, we put together machines today, you know, today up until the past few years, which are basically commodity boxes that you get from Intel with really, really nice interconnects, InfiniBand, you name it. You're programming an MPI. Now we're switching over to combination hybrid programming in MPI and OpenMP. But then at some point, we're going to have to make the switch. The switch is pushed by two things. One, these accelerator cards, GPUs, they use less energy. They're good for certain calculations, okay? And so there's going to have to be a switch where we're using CUDA, OpenCL, something like that. Who knows? Another language comes down the block. And then we're pushing towards exascale. And somewhere here, we're going to have to make this hop. And the question is, when do you want to do it? And we already know when we're going to make this change. But the change will be painful at some level. And the painful part of it will be you've got to learn a new language if you want to get the most efficiency out of the machine. And it doesn't matter. This is NERSC. It's all supercomputing centers are going to be headed in this direction. So we put together a test bed. You're always doing this. You always buy a machine that you think is going to be a few years down the road. It'll be something like this. And so we did this at NERSC to test out a few different types of simulations. Okay? And so the end of the day, the question was, what codes do we have there already that could benefit from something like GPU accelerations? And then also, conversely, what codes see no benefit whatsoever? Okay? You know, at the end of the day, if you're not getting as much out of a GPU as you are a CPU, why bother? You know, they cost more. Okay? And then the question, the real question is, the GPU swim lane going to supplant the CPU swim lane, or just expand it into different space? Are they the future? Is it just a feature that we're looking at? And should we expand in this direction for specific users? And I'll say that because there are some users that won't be able to take advantage of these. Okay, so we put together something called Drac. It had 44 nodes with the GPU on each node. They were dual socket Xenons, okay? These are the GPUs we had, the NVIDIA Teslas, okay? And then we put CUDA on there and a whole bunch of PGI compilers that could take advantage of this. And so this is sort of a schematic of the pain that you have here. There's some parallelism here. The GPU direction, the CPU, programmability, of course, is easier here, harder here. And how do you get to this goal here of having a fully programmable many-core system which takes advantage of the CPUs and GPUs? And could we get the people set up? Now, this is a really interesting slide here, and I just want you to focus on some of the numbers here. And this will get to the heart of my talk, which is why GPUs may not really be a good answer. At the end of the day, cost comes down to moving electrons across a wire, okay? 1 millimeter pushing information, 6 picojoules, okay? That's not going to change between today and 2018. 20 millimeters, 120 picojoules. A flop cost you 100 picojoules today. Of course, if you want to hit what people are pushing for exascale, which is, well, you know, you could sit down and build an exascale machine today, and it would cost 100 megawatts of electricity to run it, okay? Well, they don't want to pay that. They want to pay 20 megawatts, okay? So we know we have to bring this cost down by this type of factor. So maybe in 2018, you know, we're shooting at 25 picojoules, okay? Now, here's the thing. If you're moving some piece of memory that you want some flop to work on, okay, and it's coming off of, say, a hard drive into memory, from memory into the CPU, GPU, this is the cost you're going to be paying, okay? That's a minimum type of distance to go from the memory into the processing unit, okay? And notice what the flop costs you. So moving the data costs way more than the flop. So you have to think about this very, very hard, okay? And this is painful when you're on, not to say the simulation side, but you're on the interpreting the experimental data, which is what I am, where you generate terabytes and terabytes of data and you need to process these, because all of it has to go through this hit here. So simulators, they could say, oh, you know, I really wanted to print out this, get out this slice plot here and analyze this, and I didn't do that in my last simulation. You know what? It's cheaper just to rerun the simulation, this multiple million-hour simulation, and go back and do the analysis on that piece. Experimental data, well, you're stuck with it. You got to read it in again. We did a bunch of different domain science application areas, everything from lattice QCD to AMR, astrophysics runs. There were benefits across the area using the GPUs, okay? No tests were performed on the analysis of large data sets, and that's because nobody wanted to go through the pain of figuring out how to do this. GPUs just, you know, it is a device basically for sending a calculation down to having it pound on it for a long, long time and then spitting back a number. The thing I can use it for is FFTs in image processing. That they're really good at. Anything else, not so much. So here were some comments from some early users. First off, domain science, scientist input is essential. Debugging on these new compilers is hard. Programming was challenging on the GPU. There weren't many things there for the scientists. They were just for the hardcore programmers. Then, of course, the advanced programmers said, well, you know, GPU and CUDA, that was great. I had no problem. And they said, you know, there are some examples out there, but optimizations weren't exactly right, and compiler options and things. And mixing MPI and CUDA, straightforward, but the challenge was, of course, being the most efficient at that. And that's where very few people have experience. A lot of people complained. Disappointing. The 200 gigaflops for this matrix problem here was not worth the trade off of rewriting the program. If it's going to take you 1 year to rewrite something for a factor of 2 improvement, why not just burn the time during that year, you know? What's it going to save me? What's the real advantage? And a lot of people complained about CUDA at the end of the day for scientists. So 2 astrophysics codes that we tried out, one in AMR, another an N-body application. And those actually, they saw very nice speed-ups, a factor of 5 speed-ups. They had to work a lot with how to handle the data, where they basically had to sit back, draw up their code on a whiteboard and say, what parts of this are we going to solve on the GPU because the GPU is optimized to solve this, and then completely rewrite their code from scratch. Okay, now that happens. I watched this happen in grad school with a code which I started off with, which was 100,000 lines, which isn't that bad. I had written 10,000 lines of it, and then we threw in some MPI, and that wasn't so bad. It was only a couple thousand lines here and there. And then once people got used to it, now the code's exploded up to well over 1.5 million lines. Now, as a grad student, I wouldn't come into a code like that anymore myself, just because, you know, I couldn't read it and understand it. Modifying a code like that to take advantage of GPUs would be painful, to say the least. So we're hoping for things like built-in libraries or compilers that can figure this out for us. Wouldn't that be nice? So just figure out the best way to use the GPUs. Don't bother me with that task. Well, that's not likely going to happen. Okay, so now I switch to big data and the Palomar Transient Factory. This is there's some astrophysics in here, but it's not much, and I will explain it along the way. And holler if there are any questions if I don't explain anything. There are several large optical surveys, and by this I mean scanning the skies with CCD digital cameras. The one I'm going to talk about is the Palomar Transient Factory. There are a couple others that are out there right now. The La Silla Supernova Search is also one that we run at NERSC. SkyMapper is down in Australia, and PanSTARRS is off in Hawaii. There's a spectroscopic search where they take spectra of galaxies, stars, you name it, across the sky. That's known as Sloan 3. That's run down in Apache Point, New Mexico. The thing about these projects and why people have switched to the lone astronomer at the telescope looking, well, they never really looked through an eyepiece, but taking an image or something like that, to these massive surveys is that these are more cost efficient at the end of the day. If I can do astrophysics, which spans everything from planetary science to transient phenomena to cosmology in one survey, one package gets you everything, I'm going to do that because I will satisfy the needs of 50 or 100 astronomers rather than giving every one of those astronomers, say, 5 nights at the telescope over the year. Okay? It's just much more beneficial. The problem then becomes, how do you manage this pipeline and this analysis? So for the Palomar Transient Factory, we had competition, which turned to, well, we smoked them, SkyMapper and PanSTARRS. And they were set up to be a wide field survey that did multiple colors, spanning the ultraviolet to the infrared. And we decided we need to do something different because if we play their game, they're going to win. Okay? So what we went after is the transient sky. And we wanted to go after it on time scales that nobody else could touch. And the reason that we got to do that was because we wanted to exploit the computing facilities at NERSC in ways that these teams didn't have any opportunity to do. So we started quickly. We took an existing telescope, we yanked out the camera that was on there, and we put on this CFHT-12 camera, which I'll show you in a bit. We decided throw out doing multiple colors. We're just going to stick in a band at a time, and so we picked this reddish band, which sort of spans about 600 nanometers to 750 nanometers. Explore and get rapid turnaround on temporal domains in unique ways, taking advantage of the supercomputing that we had at NERSC, and squeeze out all the possible science that we could. So listen to the domain scientists that are in our program and say, okay, what would benefit you? Okay, write that down. What would benefit you? Write that down. Figure out a way to optimize this problem, and then give them turnaround so that they could take advantage of it. And the big thing for us was immediate follow-up, as near real-time follow-up as possible on unique transients, things that explode and you'll never see again on the next telescope sizes up, the 4 to 10 meter class telescope. So we're working here on a telescope which is just over 1 meter in size. That's our discovery engine, and we're pushing our follow-up to the largest telescopes in the world, both ground and space-based. All right, so here's sort of a plot of the decay time in days versus brightness, okay? And this is in astronomers' absolute magnitude, so I'll sort of rephrase these for you, for the physicists here, chemists and biologists. In green, yellowish green here, these are things we knew about beforehand. These are classical supernova. Supernova typically explode once every century in a galaxy like our Milky Way, and they're very bright. Some of the supernova that have gone off have been visible in the daytime in the Milky Way for months. Okay, there was a supernova that went off in 1054 that people could read by at nighttime. Okay, so these are massive explosions. Okay, classical novae are like new stars that pop up in our galaxy. Okay, so they're several orders of magnitude fainter than supernovae. But then we had all of these things which last on the time scale of minutes, a day, to a few days, to things that are several hundred days. And these were proposed by theorists, but they had yet to have been observed by the time we started our program. So, what is our camera? Our camera is a 7.8 square degree field of view camera, the CFH12K. It has 1 arcsecond pixels. An arcsecond is the resolution of a dime at 1 mile. Okay? And 7.8 square degrees, to give you an idea, the full moon is a half square degree on the size. Okay, so we started off in 2008. By that time, I had been practicing on fake images for about 1 year. We got our first useful science images on January 13th, 2009, and we discovered our first supernova about 1 month later. We have discovered over 1,600 supernovas since then. Now, if you put in a supernova goes off in a galaxy like our Milky Way once every century, we're staring at lots and lots of galaxies. We ran with 2 cadences. We run with the nightly cadence, where you're hitting the same field every single night, and you're looking for things that pop up. And then we go for another cadence, which is called our supernova cadence, sort of every 3 to 5 days. That's spread out in time so that we can get more sky coverage, okay, so that we can get more area. And here's the camera. We have 1 dead ship, which is very, very tragic, but what can you do? You push on. It's 92 megapixels, and there is the telescope, just a simple 1-meter telescope. It's been around for over 60 years. Okay? These are all the different science projects that people lead within the collaboration. It goes from different types of supernovae to these novae to variable stars of all different types, flare stars. People want to trigger the gravitational wave detectors. They'll find some transient. They'll be able to localize it to 100 square degrees. They would like us to go over and survey that part of the sky and tell them what went boom in the optical there. You name it. This is basically everything in the transient world. And these are the telescopes that we follow up with, okay? So we have this little, just over 1-meter telescope finding these sources, and then we throw them at everything on the ground, from the automated Palomar 60-inch, which can respond robotically to a command, swing over and take an image to us, to the Keck telescope, which you have to schedule months in advance exactly when you're getting. This telescope costs $50,000 a night to run, okay? Most of these telescopes have budgets on the order of $1, $2, $3, $4 million a year, okay? This is the cost of the experiment. It's not in running this survey machine. That's a few $100,000 a year. It's small potatoes. It is in being able to trigger one of these telescopes and not waste their time and money on something which is garbage. And that is what we push for. So this is the pipeline. Now, if you're writing a good pipeline, the first thing you do, and you have a large collaboration, is you set up boundaries. So these are our boundaries. This is everything that goes on down at the telescope. So we have the thing which schedules. Writing a good optimized scheduler for the night is a challenge, okay? You have the observatory control system, which basically takes weather information from outside, says it's good enough to open, is it dark, etc. You have the camera controller, and then you have the data quality monitor. You can be open and swinging around surveying the sky, and clouds come in. your monitor should tell you, no, stop looking at this part of the sky, swing over somewhere else, take some images there. If it's bad, just shut yourself down for 10 minutes, turn yourself back on, maybe the clouds will go by. We send all of that data up by a high-speed link microwave relay towers from Palomar Mountain down to the University of San Diego Supercomputing Center. They shoot their way up to Lawrence Berkeley Lab, NERSC, and also to Caltech, the IPAC, where they do what we call the quote-unquote final processing pipeline. They run about a month or so behind when we get the data. We do the real-time processing. The goal basically is to grab the data, run image subtraction on it. We have this new data coming in. We have old data that's in the can. We difference the images, and then we look for things that go bump in the night, and we classify them. We send this data out to the rest of the project in what we call a follow-up marshal, and then from there we can trigger telescopes automatically, like the Palomar 60-inch, or if people are on a telescope or can schedule a telescope, they can look at the marshal and determine what to do next. We do this by sending the data through the data transfer nodes at NERSC. We've purchased 250 terabytes on the NERSC global file system, which is a really nice thing. The global file system can talk to all of the computers at NERSC. We use Carver to run our subtractions. It's an IBM iDataplex machine. We have a database, a very large Postgres database sitting on a Science Gateway node, which basically ingests all the images, figure out what needs to be subtracted, shoves those over to Carver. Carver spits back the candidates, and then that goes out via Science Gateway node to the rest of the collaboration, where the collaboration can actually view these subtractions and get down into the nitty-gritty of it if they want to, or just ask the question, what are the top 2 or 3 things we discovered last night? Here's the database. It's broken up, of course, into individual images. The images can be combined to make a deeper co-added reference image. A new image comes in, you can subtract it from a reference. The subtracted image gets scanned for candidates that stick out, that go bump in the night. Those go into the database. We keep track of everything that we do. We have 1.8 million images up until, I think, just a few weeks ago. We've made 32,000 reference images. This is pretty much the entire northern sky that we can view. We've done over almost 1.5 million subtractions. We have 900 million candidates in the database. Most of these are garbage. 45,000 saved transients, many more unsaved. And this is what we've pushed through in 800 nights. And so this is a view of the sky that we've covered and the number of times we've hit it. We've hit most of the sky on the order of 50 to 100 times. We can't see the south here, and we don't look at the Milky Way galaxy, which is this black chunk here. Some areas, like our nearest neighbor, Andromeda Galaxy, we hit every single night it's up. So that's why we have well over 1,000 images there. We've discovered 1,600 spectroscopically confirmed supernova, 100,000 transients in our own galaxy, variable stars. I can't even tell you the number of asteroids. It's multiple hundreds of thousands. Tens of thousands of transients in our nearest neighbor, and 31. So, if you do the numbers, 800 nights, 900 million candidates, about every night we're generating 1 million candidates. Most of these are not real. These are 5 sigma detections by our scanning program. Most of them are image artifacts. They can be due to misalignment of the images, image saturation from bright stars. Out of these real astrophysical objects, 50,000 of them are asteroids. Okay, this is boring to me. I don't care about well, maybe I care about the one that could hit us. Okay, that would be one to worry about. But most of the time, boring. Okay, 1 to 2,000 of them are variable stars. About 100 supernova, but these are supernova that we already know about. Supernova takes about 20, 30 days to rise, another 20, 30 days to fall. Every time we hit that field, we'll find it again. we have about 3 to 4 new young supernova or other explosions that we haven't seen before. This is what we're after. So 1 million, mostly garbage, and we want to find these 3 or 4. So this is what a typical image looks like. Here's the new image, here's the reference image, and here's the subtraction. And if you look, and you guys have the slides available to you, you can zoom in here and look at these. These are all garbage, for lack of a better word. Each of these chips is a 4K by 2K CCD. Not so much different than what's in a very nice digital camera, except they're cooled down to liquid nitrogen temperatures, and so they're very, very sensitive. But that's basically the only difference. We take 3,000 of these every night. It generates about 50 gig during the summertime when we have a 6-hour night, over 100 gig during the wintertime. So if you look at this one image here, okay, here's the new, here's the ref. There's no way you see this guy right here. This was what we called PTF, Palomar Transient Factory 10, the year 2010, and then YGU. We have naming schemes that start A through Z, AA through ZZ, and AAA through triple Z. We actually got to 4 letters. Thank God we did not get beyond starting with A, because you can get into some really embarrassing 4-letter words if you go too far down this path. These are some of the other things that we found here. Okay? These are just saturated stars, and they leave rings around them, and then, you know, but my scanning program will come over and look at this and say, okay, well, there's something there that sticks up 5 sigma. What do we do about this? Okay? And on this image, which actually turned out to be a really, really clean image, we had 230 bogus candidates, 2 variable stars, 4 asteroids, and at the time, what we thought to be the youngest Type 1a supernova, caught just a day after explosion, PTF10YGU. That turned out not to be true. In August, we happened to be looking at a nearby galaxy, only about 18 million light years away, not too far, and we discovered PTF11KLY. And this was caught only 11 hours after explosion, about 1/1000th the brightness that it reached at peak. This was a supernova you could actually see in a very good pair of binoculars. Okay? We hadn't had one of these in 40 years. We were able to confirm it very quickly, and this was not found in our standard methods. Basically, I was feeling sort of embarrassed about how the pipeline was running the previous night. Somebody decided to upgrade the compilers on Carver, and my entire pipeline broke. They didn't think it was going to do anything, okay, and it destroyed everything. And so I was playing catch-up in the morning. So I just queried the database once I got all the subtractions in there and said, give me the best target in a known nearby galaxy that we have. And this is the one that came out. And we sent it off. Now, this is a bizarre run. This is also something one should learn about pipelines. You must be intimately familiar with them, and they can't be CS projects, okay? You have to be invested in their success, okay? That night, we were doing a G-band run. We weren't doing this reddish band. We were doing a blue band. We hadn't had much references in there, so we actually only had about 500 square degrees to subtract. It wasn't much. We found 10 new transients that night, and the pipeline, as I said, was running slow due to this kernel update. Also, we had an IP address at Caltech, the Marshall, which handles all of our discoveries, and that was screwed up. Somebody decided to move the machine across the machine room floor down at Caltech, and they screwed things up, so we had to save things by hand. Okay? So, I was going through, along with Josh Bloom, saving things by hand, and boom. He found this lovely thing right here. I found this guy right here just a couple minutes later. We're just going through the data, and I'll show you how we do this and how we hope our computers normally do this and have been doing it all but, say, a dozen nights. And this is the type of discovery where the domain scientist is invested in seeing a turnaround immediately. Okay? Here's the image taken the night before. Here's this guy right here. There was a 20% rise in just the first hour. This gave us our first clue that this thing was screaming up and was very, very young. And then we turned it around in 3 hours from the time we made the query, discovered the object, to having somebody take a spectrum of it. Okay? Mark Sullivan, of course, is this astronomer over in England. It's always great when you're in the field of astronomy to have collaborators spread out over the world. Somebody's always awake. Somebody can man a telescope when, you're getting ready to fall asleep. He had a telescope which he could command robotically that was sitting on the Canary Islands, and it was just becoming sunset there, just as I had made this discovery back in California. And Mark was asking, is this real? And I could go through the database really quickly and say, yep, we have 2 detections. It's real. It's not an asteroid. I didn't think it was going to be a Type 1a supernova. Just a few minutes later, he threw it into the Liverpool telescope Q, and he said, you got to love robotic schedulers. It just sucked in the data and said, go. He saw it in the acquisition image, and right after that, we were able to trigger large ground-based radio telescopes, CARMA and EVLA. We triggered the Hubble Space Telescope and the Swift Telescope, all within 3 hours. Now, typically, what our users see is something like this. They get those 3 images, they get the zoom in, and then they can do this for any candidate at all in our database and take a look at it. We also have a robot that goes through. It uses a lot of additional information. It'll take the position of the object on the sky and then query about 25 different databases which are spread out all over the world for what contextual information do I have about this part of the sky. All the observations that were done there before, people who have gone through and, say, taken a spectrum of a galaxy in that area so they know how far away this object is, you name it. And it comes back then with a Bayesian classification scheme of what is this object likely to be. Some sort of circumnuclear event. Okay, that's an active galaxy, a massive black hole that's sucking in material. They sort of burp up and down for hundreds and thousands of years. Okay, those are sort of boring. A variable star, okay, just something that cruises up and down by a factor of 20, 30% in brightness in our own galaxy. This robot goes through every single candidate and classifies them, and then pushes out the best ones on the web to the rest of the collaboration. Now, the machine learning classification algorithm that they did is rather complex. This is just for stars. These are like the 25 or 30 variable stars that we know of today, and it takes in all the data that we have on this object, all the contextual data that we have, and then does this machine learning classification algorithm that says, okay, at the end of the day, we're honing in on these are the 2 best classes of objects, and this is what I think it is, and we'll spit this classification back. And then it keeps track of that, and as more data comes in, say we trigger a follow-up telescope, and it obtains additional information, it can then use this to hone in on then what is the best object this is and tell the rest of the collaboration. Now, in addition to this, we have one of these for active galaxies, we have one of these for supernovae, we have one of these for novae. So this is multi-dimensional, and this runs on, well, not every million objects, but it runs on several thousand objects every single night. We also did a project called Supernova Galaxy Zoo. I don't know how many of you have heard of the zoo universe, but this is what they call citizen scientists, and they use the zoo to look at everything. They started off with a galaxy classification project where they were just having people classify galaxies by eye. They've gone on to things like translating Greek text that they found on papyrus scrolls in the British Museum. They scan these things in, they put them up on the web, and then people go in and type the things, because OCR does not work on these old texts, okay? They have people, I mean, you name a project, you propose it to them, they'll do it for you. We did Supernova. And what these guys are really, really good at is honing in on what questions do you ask a citizen scientist. And so we decided to send them the triplet of images, the new, the reference, and the subtraction, and ask just 4 questions. The questions were, does there appear to be an object in the center of the crosshairs there that looks roundish and looks real? Did the object subtract well? Did other objects in the field of view here subtract well or reasonably well? Does this look like a point source, something that's very small? Does it look extended? Okay? And they would go through these series of yes or no questions, click, 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 and then it would get a score based on that. And if it looked like there was a nice galaxy and an object off to the side and it subtracted well, it would get a very high score. And if it failed on any one of those, it would get a lower score depending on where they bowed off. These guys are really, really good. There are about 20,000 people signed up for this project. We send about 200 off of these each day. And they go through, and I would say in just a couple hours, they classify everything. And we usually wait till we get 20 people to classify every object, because not everybody is as good as everybody else. Okay, I can go through and classify these things in my sleep, and okay, I won't say I'll score 100, but I'll score 99.9, okay? I've been doing it for a long time. Many of these classifiers, and we note this because we can keep the time and their location down, fall into 2 species. One, break time at lunch. I want to just do something because I'm bored, okay? And you can see that there's a spike in scanning at that time. The other one is I've come back from the pub at night and I don't feel like going to sleep. And we also note that the quality of the subtractions is much better during the middle of lunch than it is at, say, 12:30 at night, okay? And back before Britain passed their laws on when the pubs can close, now they're open all night long. It used to be they closed at 11 o'clock sharp. You could see this spike at 11:30. It was absolutely ridiculous. And the quality was... But we tested these guys out, 3 years ago. We sent them 12,000 supernova to classify. And they actually went back and found several that we had missed. And it was really, really nice. It proved that these guys could do something. We actually just shut them off 1 week ago. And the reason we shut them off is because we retrained our robots. Here is a plot of the human zoo score versus our machine-learned zoo score. Of course, once you have a whole bunch of images and a whole bunch of ratings for these images, you can write your own machine learning algorithm that can say, I can take now all of these scans by all of these people and all of these ratings and figure out a new way to score them based purely on machine. And the great thing about it is repeatable. It is something which you will get an answer out of a certain purity every single time, and it's of good quality, okay? And basically in red, what you want to see here is once we get up above a level 1, these tend to be all really good candidates. Over here, it's about 0.05, and everybody was able to say these were good. If you look at an ROC plot where we looked at the misdetection rate versus the false positive. So in the ROC plots, for those of you who are not familiar, you want to drive yourself towards 0, 0. That I have found every single good candidate and I have not reported a candidate which is bogus. Okay, so you want to drive yourself this way. The human zoo score looks like this. Here is our machine learned. And the difference is we weren't, because of the way the laws are in Britain where the zoo project is, we're not actually allowed to test the scanners. That's considered performing a psychological test on somebody without their knowledge, which you can't do, okay? We could, of course, say who's a good scorer and who's a bad scorer. And of course, every now and again, out of the 20 people that we require, you just randomly will get 10 really bad people rating, okay? And that's why they're not as good. Even though we're using their data to train ourselves, we can be better because we could go through after the fact and say, who are the good ones and who are the bad ones, throw out the bad ones, and then retrain. And this is an iterative process, and so that's how the machine learning score is much better. This takes about 3 seconds to run on every single image, okay? The images come in. We first process them, which is just to take out background electronic issues. That takes about a minute per image. We run a subtraction. That takes about 2 to 5 minutes, depending upon where you're looking in the sky. An extragalactic field, it can be pretty quick. In our nearest neighbor or in our own galaxy, there are many more objects, so it takes longer. So somewhere on the order of, at most, if everything's working perfectly, about 10 minutes later, we have a bunch of candidates to look at, and it just takes a few seconds to run this classification scheme on and then throw this information into the database, and then you can say, give me the best objects out of here. So we use this thing, this classifier, and we call it real bogus, okay? Are you real or are you bogus? And the level down here doesn't mean much of anything other than 99.9% of the objects fall down below a level of 0.07, and they're bogus, almost every single one that we've looked at. Here I've plotted the number of supernova versus this real bogus score here. Only 5% of our type 1a supernova detections have a real bogus score of less than 0.07. Okay, so that means 1 in 20 times we'll miss a type 1a supernova. And usually that's due to the fact that it's very, very low signal to noise. It just got up above our threshold, and it's sitting on top of something bright. And because of that, it just looks a little spurious and doesn't fall through. However, if you require 2 detections, it goes down to 0.1% of the time. And that's pretty good. As long, we're up there 99.9% of the time, we require 2 detections. We're not going to miss one, okay? So, percent increase. So like I said, if a blip goes up and it's 5 sigma, but it's just a very, very low percent increase, we can look at this plot here, which is the percent increase versus the supernova detections that passed our real threshold, which we thought is real. Okay? And in blue are the ones we say are good. In red is everything. And so what you can see is down around the 10% level, we only discover 50% of the objects. Okay? 50% make it. Out of this total of 40, we're finding just around 20. Okay? But as we get up to 25%, we're finding the vast, vast majority of them, okay? And then if we look at bright objects, magnitude 19 in general is like a signal-to-noise 10 or 15 object, okay? And for those, we're pretty much complete all the way down to the smallest rise above, say, a background galaxy or whatever, okay? Turnaround, okay? So this was our key thing in towards beating the competition. How quickly could we turn around? This is a plot of the time from observations to having candidates in the database classified with the machine learning zoo algorithm, and I think this was for June of last year, 2 years ago. You can see when everything's working perfectly, you can sort of get them in 10 minutes. In general, due to the queue policies at NERSC, how long it takes to get something in there, it's about 20, 25 minutes, and there's a tail that goes out to about an hour, okay? This is nice. So 30 minutes after the observation, half the time, we can then say, boom, here's a good candidate, trigger a telescope robotically, or send an email alert out to somebody who's on the other side of the Earth where it's dark and say, go ahead, take a look at this. Or conversely, where it's light and they're awake and it's dark on our side and they can do something about it. So this was our boon, and we've been able to do this and maintain doing this ever since early 2010 to today. Here is an example of this pipeline and how we've turned around. So we have a detection here at the Palomar Transient Factory and the automated discovery classification done within 30 minutes. A manual alert at the Weizmann Institute was then looked at, and then they were able to trigger a telescope as the sky turned around and it got dark in the Negev Desert in Israel. They confirmed it photometrically. They were able to then trigger the Swift Space Telescope for ultraviolet follow-up and the Gemini telescope for spectroscopic follow-up. And then they triggered a radio telescope on the Earth, all within about 36 hours. And what they were able to do is discover one of the youngest Type 2 supernova, caught literally just a few hours after explosion, and get a data set which nobody had ever had before. So these are the transients that we found. And if I have a plot here, now this is the first one I showed you, sort of the characteristic time scale versus the luminosity. In gray are the ones we've known about. These are all the new classes of transients we've been able to discover due to this pipeline, due to be able to get the rapid turnaround on it to stay on top of this data. Some of these transients, note, they take hundreds of days to evolve. So it's not only a matter of getting rapid turnaround on it, but it is in maintaining your database and all the images so that you can follow things for months and years. Okay? The next generation survey, what we're worried about here is we want to increase the size of the number of detectors by a factor of 5. Okay? This poses a lot of problems. We also want to squeeze down on the turnaround to make it about 10 minutes tops. Okay? We would like to, rather than going out and querying all of these 25 different astrophysical catalogs that are on the web, we'd like to ingest them all locally and have them spinning so we can query them in real time. And then we'd like to be able to handle triggers from Advanced LIGO, this gravitational wave detector, the neutrino detectors in Antarctica or at Kamiokanda in Japan, you name it. So these are sort of, speeds that we get in processing data. Sending it up to the observatory is probably going to be the biggest one. Handling the turnaround in the database might be the next biggest one. This is the problem that we have. Brightness versus time. Here are our upper limits. Upper limits tend to go like this on a detection. Red is a true variable source. So here we're not detecting it. Okay? This object is too faint here. And this is, say, when the moon comes up. The sky's brighter, we can't get as deep. Okay? Now the moon goes down, and then boom, over here, this is where we make our detection. Our detection threshold is now well below the object, and we found it here. Okay? So, all of these limits we have in our database. Okay? This is a boring transient. This is just a variable star that's just bopping up and down. But if I look right here, what do I see? All of a sudden I see, hey, there's an object here which I've never seen before. All of a sudden appears, and it's getting brighter. This looks like a real interesting transient. Right? We do waste a decent amount of time on objects like this. Okay? The problem is, we would like to be able to go back and in as near real time at all as we can add some of these data sets together, because if I add in a whole bunch of 5 sigma data points, okay, I can go much farther down and detect this object. But that requires real processing on a lot of things and keeping track of that. And that's very, very challenging. So let's see, I just got a minute or two left here. One of the things we pushed at in supercomputing 2009 was the use of SSDs as the backbone for our database. And we used a machine called Dash, which is the predecessor to Flash drives, at San Diego Supercomputing Center. They're very nice. Think of the flash drives as basically a factor of 10 more than your regular hard drive, and a factor of 10 less than memory. Okay, so it's very, very nice to put the databases on here. And if we want to go through and ask questions of all these different databases and have them spinning locally, a flash drive may be a good way to go. Another way may be parallel databases, but parallel databases with embedded analytics, so we can ask these machine learning questions. Okay, this would be a real challenge. And I'll wind up here with looking at the future. And the future is, for us in transient astronomy, is LSST. Here, instead of looking at 100 gig a night, we're looking at 15 terabytes of data per night. Okay? Now, I told you right now we're using 4 and 10 meter class telescopes to follow up these objects. Okay? They're expensive. But we're finding objects with a 1 meter class telescope. They're really well suited. LSST is on the order of 8 meters. Okay? It goes much, much deeper. You need a telescope of, say, 30 meters to follow this up. There's only going to be one 30-meter telescope in the world at the time. Okay, so now I go back to that problem where I have this transient that's just popped up, and I've just seen it. And it's really, really faint. And this 30-meter telescope, and by the way, that telescope's going to cost $100,000, $200,000 a night to run. Do I send this new object off to it before I'm able to ask this question? And oh, by the way, 15 terabytes of data, I'm going to be finding objects like that. Well, the 1 million bogus things that I have, it's going to be 100 million bogus things. And the 3 to 4 interesting objects is going to be hundreds. Which one of those hundreds am I going to send? That's the real challenge for us to get through over the next year. I'll stop here and take any questions. Thanks.